All right, so let's do some examples. So this first example, we've got a voltage source connected to a resistor and an inductor with some values here. And the voltage is 500 cosine 377t. 377 is the frequency, omega, which is 60 hertz. So it's a common power number in radians per second. We're supposed to find the power P, the reactive power Q, and the apparent power, so the full power triangle that's delivered by the source. So what's coming out of this, because there's power coming out of here, going into here, and into here. So when we talk about power, you want to be specific about where the power of what is an important thing to see. So power delivered by the source. Our plan, we are going to first find the impedance of the load, the total thing, R and L together. We'll do phasors for the current and for the voltage, and then we will get the VRMS and IRMS that we need, and theta. And once we have those three numbers, we can use the definitions of P, Q, and apparent power to find the answers. So why don't you try this, pause the video, write it down, and on a piece of paper see if you can find the impedance of the load. It's combining these two impedances with this omega. Then find I and V as phasors, and VRMS, IRMS, theta. See if you can do that. That would be a really useful skill. All right, so here's how I did it. First, finding the total impedance of the load as opposed to the impedance of the inductor here. I've got two ZLs, it's really bad. But we've got ZR is 100 ohms, ZL is J omega L. It's a 0.03 Henry inductor. So 100 plus 11.31 J is our total impedance of our system. That's in rectangular form. We can write it down in polar form, 100.64 with a phase of 6.45 degrees. So this is theta. The angle of our impedance is theta. So theta is 6.45. It's greater than 0, so we call that lagging or inductive. We had a resistor and inductor, so it makes sense that it's inductive. Theta greater than 0. So we found the impedance. Now we can find the phasors for the voltage, which is just given to us, 500 with a phase of 0 degrees. And the current is V divided by impedance. It's Ohm's law for phasors. So if we take 500 with a phase of 0 divided by 100.64 with a phase of 6.45, that's our IM right there, 4.97. And our theta, we always have negative theta in the I. So we have a positive number in Z, we get a negative in I, because we always assume that V has got 0 degrees and we're dividing here. So remember that, negative theta, positive theta. Anyway, 500 is our VM, so divided by the square root of 2 to get VRMS. 4.97 is IM divided by the square root of 2 for IRMS. So amps and volts there. Is that how it worked for you? I hope so. All right, now we've got all of the numbers. We just plug into our formulas. So the power factor, which wasn't actually asked for, but it's good to think about. Cosine of theta, so 99.3% lagging. So this would be 0.993. And because theta is positive, it's lagging. It's kind of the opposite of what you'd think. P, VRMS, IRMS, cosine theta, 1234.2 watts, so a little over a kilowatt. Q, the reactive power, this is the one that averages to 0, but sometimes you have to pay for. VRMS, IRMS times sine theta. Because theta is so small, this is small too, so 139.6 And the units here are VAR for reactive, not watts. The apparent power is VRMS times IRMS with no theta term in there. So 1242 and its units are VA. All right, so how did that go? Did you get it right? All right, so this is another example of a design problem. And this is a common one if you're running a big industrial plant, like if you work for Tesla's auto assembly plants or something like that. Anybody using a lot of power. The setup is we've got a voltage source, so this is our power supply to the power plant, to the manufacturing plant, we'll say. And there's a load here, Z, given as 2.5 with a phase of 75 degrees, so that's the phasor for Z. And our voltage is 1,000 times the square root of 2 cosine 377t. So again, this is omega 377 radians per second. So what we want to do is we want to add a capacitor on top of our load, so right at where the power comes in, to balance it out to make the power factor 100%. This is going to make our Q 0, and so if we're paying for Q, remember Q doesn't do any work, it averages to 0, but the electric company may charge you for it. So we add a capacitor, because this is mostly inductors, we add a capacitor to make that power factor 100%. So there it is, a power factor of 100% minimizes the cost of the reactive power, which doesn't do any work, you just get charged for it. The load has a positive theta, 75 degrees, so it's already inductive and lagging. So what happens is instead of the power coming into the inductors and then back out to the power company, into the inductors, back out to the power company, that reactive power is doing that. The power company charges up your inductors, and then it goes out of the inductors and into the capacitors, and out of the capacitor and into the inductors. So you're storing the energy internally, so PG&E didn't have to deliver it to you, and they don't have to charge you for it. So we add these capacitors. Inductive loads are more common in an industrial setting if you had a bunch of mills or robots or anything. If they've got motors, then they probably have inductors, and so most of the loads tend to be inductive. So this is a realistic example. All right, let's see our approach, and then you can take a stab at it. So the first step is going to be we want to find the power angle theta, including the capacitor. So for the whole factory here, our original load plus the capacitor, what's theta? And then we want theta to be 0. That gives us the power factor of 1. So we'll solve for the capacitor. So that's the steps. So why don't you pause the video, get yourself a scratch sheet of paper, and give it a try. Oh really, go do it. Go try. Try it. Okay. So here's how I did it. We've got the impedance of our system. We've got the load Z and the capacitor's impedance. They're in parallel, so we combine them with the 1 over the 1 overs. Even capacitors combine like this because we're doing impedances where everything uses resistors formulas. So 1 over, this is the original impedance, 2.5 with a phase of 75. And the capacitor's impedance is 1 over omega c with a phase of negative 90. So it's 1 over a bunch of 1 overs here. So, but we're going to do this division in the polar form, and we get down to this next line. So 1 over 2.5, where we get the 0.4, and a phase of 0 minus the phase of 75, we get a phase of minus 75. 1 over omega c gives us omega c, and the 0 minus 90 gives us the plus 90. So here is the total impedance of our factory with the capacitor. We have to add these now, so we want them in rectangular form. So that goes down here. So 0.4 with a phase of minus 75. This is 0.4 times cosine of negative 75. This is 0.4 times sine of negative 75 times j. The old phasor conversions, omega c with a phase of 90 becomes j omega c. It's all in the imaginary axis. Now we can add them together. There's only one real part. We can combine the imaginary parts here, and that gives us our total impedance Z for the factory, including the capacitors. All right, so we're trying to find the phase of this, and the phase, we could put this in polar form to do the division, but we can realize that the phase of Z is going to be the negative of the phase of this, because it's going to be 0 minus the phase of the denominator. So the phase of Z is negative the phase of the denominator, and that's what we're caring about. We want that to be 0. So the phase of the denominator is the arctangent of the imaginary part, omega c minus 0.3864, divided by the real part, 0.1035. Here's the minus sign that come down from here. So this is the phase angle, the power angle. We want to set that to 0, so this top has to be 0. So omega c has to be 0.3864. Solving for the capacitor, 0.3864 divided by omega, which is 1 millifarad, 0.001 farads. So this is how much capacitance you'd add right where your power comes into your factory, and that will cause your charges from the power company for the reactive power to go to 0. So it's worth adding a little capacitor to save you some money if PG&E is charging you for that. At your home, they don't. So, but at a lot of big industrial clients, it's an important thing to consider. All right, so that is the example. I hope you got it right. I hope you can do these two problems. There'll be similar ones on the homework assignment to try and do reflections on. Hope you're doing well and staying healthy, and I will see you later. Don't forget to like and subscribe and hit the bell. The bell. No, I'm just kidding. Watching too much YouTube. I don't care if you like or subscribe this video. I just hope you do the homework, and see you later.